Okay, so you can refer on week 14 for the exercise. So we will discuss this exercise today as your preparation to answer the final exam for question 1. Okay, so here is the exercise. So today we will do the exercise on lead and lead. So we already do the exercise on Zeclanicus for question number 2. So for question number 1, so you need to answer the lead and lead compensator. Okay, so I give you in this exercise, so 3 questions related to lead and lead compensator. So first we look on the first question here. A mobile robot suitable for nighttime guard duty since the robot never sleep and tired. So the steering control system for the mobile robot can be simplified and represented in figure Q1A, and figure Q1B show the block diagram of the system and the unit step output response of a second order system respectively. So the question is, so you need to analyze the system performance by determining the percentage of overshoot, peak time, settling time, and steady state error. So after that, you need to design the key gain value for the output response. Okay, so this is the output response. So if you remember in control system engineering, so we already learned how to obtain the TPTS percentage of overshoot by using the output response graph. So the question asks us to find the percentage of overshoot. So from here, we can obtain the percentage of overshoot by using the formula. The formula for the percentage of overshoot is given by C maximum. C maximum is the amplitude maximum. So from this graph, so the magnitude maximum is about, so we can say yes, it is about 1.62, maybe 1.62 minus C final. So divide by C final multiply with 100%. Okay, so from here, so our C final is somewhere at here. So maybe we can put our C final. So 0.9 is here. So our C final is about 0.98. So the C final here is about 0.98. So next we just substitute the values. C maximum 1.62 minus 0.98 divide by 0.98 multiply with 100. Okay, so dapatlah the answer for the percentage of overshoot. Dapat it's about 65%. 65.3%. Okay, so next, the question asks us to find the peak time. So peak time directly. So we from the C maximum. So the T on the C maximum is our peak time value. So from here, so our peak time, so we can say is about 0.25 is somewhere at here. So kita tambah sikit lah, 0.28 second. 0.28 second. And then we need to find the time settling or settling time. The settling time, so basically we measure the settling time plus minus 2%. 2%. So if we assume that the plus minus 2%, so that's mean you need to find the C with plus 2%. So that's mean we put it as a C 1.02. So 1 is our C final. So since that our system plus 2%, so we make it as a 1.02. So we multiply C final, multiply with 1.02. And then for the C minus 2%, so it become as a C 0.98. So we multiply C final with 0.98. Any question? Boleh? Boleh faham ke? So ini kita dapat lebih kurang 1. So for C 0.98, so the answer is about 0.96. 0.96. So after that, you need to draw the line on this graph for amplitude 1 and 0.96. So 1 is about here. So you just draw this line. And another line at 0.96. Okay. So after that, we observe the signal. The signal must be always in between these two lines. So the first point that cross the line is our TS. Okay, so for this case, so TS is found somewhere at here. So dekat sini, so maybe we can put as a 0. TS is equal to 2.8 second. It's about 2.8 second. Faham eh? So next, so we need to find the steady state error. So steady state error, so from here, so we can obtain the steady state error from the graph ESS is equal to 1. 1 is our input, since that the system is a step input. So that means our input is 1. So 1 minus 0.98. So the ESS is considered as a 0.02. 0.02. Okay. Okay, so we already analyzed the system performance by figure Q1B. So the next question, we need to design the K gain value for the output response. Okay, so remember, so if I'm talking about the K value, so you always start with the formula. K is equal to 1 over G H, and we put it as a magnitude, and we replace S with ST. So that's mean if we want to design the K gain K value, so we need to have first the ST location. So before this, the example the example that we have done to find the ST location, so we will refer to the root locus. But different with this question. So since the information given here is the output response, so not the root locus, but we still can obtain the ST location, since that we know the ST, the general formula for the ST is given by minus zeta omega n plus J omega D. Okay, minus zeta omega n plus J omega D. So what we do have just now, we already have the value of TP, TS, percentage of overshoot. So definitely from this value, we can have the value of zeta and also the value of omega n. Okay, so remember the formula. So it's the formula for the TP, for the underdam. So TP is equal to pi over omega D. So definitely from here, you can obtain the value of omega D. And then we also have TS. So TS, the formula for the TS for 2%. So for plus minus 2%. So the formula is given by 4 over 2 zeta. Sorry. 4 over zeta omega n. Okay. So from the value n, the value of TP and TS from this graph, so we can obtain the value of omega D and then the value of zeta omega n. So from here, so definitely we can obtain the ST location, and then we can evaluate or we can design the K value for this output response. Okay? Okay ke semua? Kelas? Ada ke? Oh, ada ke ni lagi?
Ada.
Ada? So boleh faham
Faham, Doktor.
Boleh faham
InsyaAllah.
InsyaAllah. So please remember, so if the question asks you to design the K, so we always start with this formula. So you need to use your so you need to use all the information given to obtain the value of ST. So if the information given is the root locus, so definitely you can find the ST from the root locus. But for this example, so instead of the root locus, so the information is the output response. But from the output response is actually we can obtain the value of TP and TS. So from the value of TP and TS, we can find the value of omega D and also the value of zeta omega n. So after that, so we can obtain the value of ST using this general equation. So after that, use your calculator to find the value of gain K by substitute the value of ST in the equation. Okay, faham So ini jangan fikir nak buat let lah, leak lah, sebab definitely in this question, they ask you to design the K gain value. So jangan pula ada yang buat lead or let Okay. Okay, next. B. Suggest and design a suitable controller to yield half of steady state error in uncompensated system. So this is our design requirement. So the design requirement is based on the steady state error. So remember for the steady state error, so we can choose the PI or lag. since that we just need to reduce half, so that's why we choose the LED compensator. Okay, so we choose the LED compensator. So the design requirement here, to read half of steady state error in uncompensated system. So uncompensated system is always referred to the K gain controller. So K gain controller that we already designed in A. In A. So from this statement, so the mathematical equation that we can write is here. So ESS new, the ESS that we want to design. So I put it as a ESS new equal to ESS all divide by 2. Okay, 2 because of half. Kalau dia sebut kata quarter, so that's mean you need to divide by 4. Okay, so it depends on the question. Okay, so ESS new is the ESS desired, and ESS all here refer to the ESS that we obtain from the K gain controller. From the K gain controller. Okay, so that is the mathematical equation from the objective in the question. So now we already decide that the suitable controller is the lag controller. Okay, lag controller. So remember first, you just write the general equation for the lag controller. So for the lag controller, so we will add a pole and a zeros. So I put it as a Z lag as a K S plus Z lag over S plus P lag. Okay. So when we want to design the controller, the lag controller, so that's mean we need to know the location of Z lag, P lag, and also the value of gain K. Okay. So to design the lag controller, so the first step, so you need to write so ni first step. The second step, so we need to write the equation or the relationship between Z lag, P lag. Okay, first, so we look again for this system. So it mentioned here since that the output response is the step output response. Step output response. So that's mean the input for this system is the step input. So for the step input, so the equation that we will use is the KP. KP means that the static error constant for the step input. So we write, so the KP new, we mentioned about the KP new over KP all. Ini awak kena remember. So the formula or the equation, this equation is not given in your appendix. KP all equal to Z lag over P lag. Okay, so from this equation, so that's mean we need to find the value of Kp new and the value of Kp all. Okay, Kp all is refer to the K gain controller or to the uncompensated system. Okay, Kp all, and Kp new is our is based on our design requirement. So first, we find first the KP all. Okay, so KP all ataupun KP uncompensated system. Okay, the formula for the KP is given by limit s to 0 K GS. Okay, limit s to 0 KGS. So we already designed, we already obtained the value of gain K in the A question. So we just use the value of gain K here. So you just masukkan saja. And the GS is referred to the transfer function in here. Okay, boleh eh? So just put the value of gain K and then we replace S with 0. So that's mean we have here K multiply with 15 over 1 multiply with 1 for 10. Okay. Okay, so we already obtained the KP all. And then you need to find the KP new. KP new. So KP new, so how to obtain the value of KP new? So always refer to the design objective. Design objective. Okay, so we already write the equation for the design objective. So ESS new is equal to ESS all over 2. So what is the value of ESS all? So ada yang boleh bagi tahu saya tak? Tadi kita dah dapat kan? Yang mana ESS all? Nak ambil nilai mana? So which value?
0.02.
Yes, 0.02. So we already obtained the ESS from the question A. So 0.02 divide by 2. So dapat 0.01. Okay, so this is the ESS new, but our objective is to find the KP new. So how? Because we have the relationship between the ESS and the KP. So the formula is given by ESS new equal to 1 over 1 plus KP new. Okay, so that's mean you just rearrange this equation until you obtain the value of KP new. Simple kan? So after that, we already have the value of KP old, KP new. So we need to find the Z lag and P lag. So how to find? So basically, we will assume either Z lag or P lag, but basically we always assume the value of P lag. So you need to assume step number 2, number 3. Kita assume P lag equal to 0.1. Basically, you need to choose the value close to the origin or near to the origin. Must be choose near to the origin. So basically, we just choose P lag is equal to 0.1. So from here, we can calculate the value of Z lag. Betul? Betul eh? Z lag is equal to KP all KP new over KP all multiply with P lag. Okay. Okay. So we find the Z lag and the P lag. So lastly, we need to calculate the value of gain K. So any value of gain K, so always use this formula. 1 over GSH has. But for K lag here, so you need to include the P lag and Z lag into the equation. So that's mean our G is come from S plus 1, S plus 4, S plus 10 over, so we have a 0 at S plus 15. And then you need to include the P lag, so P lag S plus 0.1, and also the value of S Z lag, S plus Z lag. And then we just replace the value of ST. We assume the ST here is same with the ST with the K gain controller, since we didn't want to change the transient response. So ST here is referred to the ST for the uncompensated system or K gain controller. So you will basically you will obtain the answer definitely almost same with the value of gain K at here. Kita akan dapat lebih kurang sama je. Kalau berbeza sangat tu, salah kira lah tu. So any question? Boleh? Ada confident to answer the lag compensator? Boleh?
InsyaAllah boleh kita.
Okay.
Okay.
Okay. Awak ni bagilah respons. Sedih saya.
Boleh.
Yes. Macam itulah kita nak. Semangat. Okay. So next question. So then suggest and design a passive controller. So kalau passive controller, so either LED, lead or LED lead to yield 15% of overshoot and settling time 2 seconds for a step input. So for this question, so what is the type? What is the suitable controller to design? Controller apa? Kita nak pilih ni.
PI.
PD.
PI. P. P. PI. Awak ni lagi apa?
PD.
PD. Ni yang sesuai. Is it this is a suitable controller?
Suitable PD kot.
PD code. Okay, PD code awak ni. Sedih saya tahu.
Sebab PI dia nak, kalau PI dia nak ESS apa ni, zero kan. Tapi dia tak mention pun steady state zero. So mungkin PD lah rasanya.
Mungkin PD. Salah.
Lek.
Lead lah awak. Lead tu.
Lead.
Sebab tu kita belajar dari
Okay,
kesilapan.
first, PPI and PD is known as a active controller. So the question here mentioned about the passive controller. So for the passive controller, we go to the either LED, lead or LED lead. Faham?
Faham.
Okay, next, we look on the objective. So as your friend mentioned about, so the suitable, the objective here is to improve the transient, because it mentioned about the settling time and the percentage of overshoot. So, not in the steady state error. So that's mean the most suitable controller for this question is the lead. P and C is not related. It's not related. So different question or different objective. Boleh nampak? So for this question, so the most suitable controller is the lead controller. Kat sini pun dah cakap tau exercise ni. Lead and lead ada yang sebut PD lagi, P lah, PI lah. Aduh, awak ni. Boleh?
Kena tangan budak-budak
Boleh
ni.
kata. Boleh. So lead controller, lead controller because of the passive controller, and then the design objective is to improve the percentage of overshoot and also the settling time. Okay, why we cannot choose the K gain controller or P controller? Because the settling time here is 2 seconds. The objective for the settling time must be 2 seconds. And also the percentage of overshoot must be designed 15% of overshoot. So that's why the lead controller is the most controller to need to design. So ingat tak how to the step how to design the lead controller? So do you remember? Ingat tak? Dia sama. Dia exactly same with the PD controller. Dah study ke belum ni? Belum. Okay, ni jawapan tadi ya. Saya tak nak bagi. Awak buat sendiri. So this is how we design the lag compensator. So find the value of KP old. So after that, we find the value of KP new based on the design objective. And then we choose P lag. And we can obtain the Z lag. And lastly, we find the value of gain K where we include the Z lag and P lag into the equation. Okay, so for the lead compensator, question C. So first step, so we write the transfer function for the G lead. So the transfer function is given by Ks plus Z lead over S plus P lead. Okay, so so before this, for the lag compensator and lead, so the key point to design lag compensator, so is the equation of the Kp new over Kp old. Sorry, Kp old Saya pun dah tak ingat. Kp new over Kp old equal to Z lag over Z lead. Sorry, P lag. Okay, but for the lead compensator, so the first thing that you need to find is the ST compensated. Okay, so ST compensated. So how to find the ST compensated? It based on the information. So if the ST compensator is not given in the question, so you need to find the ST compensated based on the design requirement. So ST compensated, so the formula for the ST is same. ST compensator, ST uncompensated, the general formula is same, minus zeta omega n plus J omega D. Okay, first we look on the question. So on the question, dia kata to yield 15% of overshoot and settling time 2 seconds. So this is our design requirement, or we can say that this value is our desired values. Desired values, our compensated values. Okay, because we want our system to have this kind of values, this kind of values. So that's mean the settling time given in this question is our TS compensated. So our TS compensated. Okay, since that from the question, based on our design requirement, so we already have the value of TS compensated from here. So using the formula of the TS, so we can obtain the value of zeta omega n. And also given is the percentage of overshoot. So from the percentage of overshoot, we can determine the value of damping ratio using the formula. This formula is given, so no need to memorize. So dapat 0.517. So after we obtain the value of zeta, so you can obtain the value of omega n using this equation. So we have zeta. So from here, we can find the value of omega n. And lastly, you can calculate the value of omega d using this formula. Okay, so you can refer. I think I already upload the appendix or the formula that will be given in your final exam. Ada kan saya dah upload kan? Kat mana? Dekat sini ya? Ke dekat assessment ke? Saya tak bagi lagi appendix. Oh, tak ada So I will give you, so after that I will give you the appendix, the appendix that will attach in your final exam. So you can see the formula, which formula you need to memorize. So which formula no need to memorize. Okay, so after that, you can calculate the value of omega D. So lastly, we can obtain the value of ST compensated. So ni ada J lah. So remember, the value here is zeta omega n. So please, so dalam in your midterm test, so mostly of you, bukan mostly lah, so ada yang ambil, dia tersalah ambil the value of zeta. So please be careful. So the value here is referred to the value of zeta omega n. So please remember zeta omega n and then plus j omega d. So after that, after we obtain the value of ST compensated, so we draw all the poles and zeros from the system and also from the lead compensator on the S plane. Okay, basically for the difference PD and lead compensator. So for the lead compensator, we need to choose either Z lead or P lead. So we need to choose or we need to assume. Okay, so in your final exam, so I advise you to choose the Z lead. We choose the Z lead and make sure you choose the Z lead same location with the poles from the system. So for this case, so this is our system. So we have pole at -1, -4, and -10. So I advise you to choose the second values of the post location. So for this case, so we just choose the P lead, sorry, Z lead equal to 4 because we want to obtain the zero pole cancellation. So when we obtain the zero pole cancellation, so we can reduce our time to calculate the angles. The angles. Okay. Okay. So for this case, so I choose Z lead at 4 for the zero pole cancellation with the system, and then we draw. So we have from the system, we have a pole at -1 and -10. Okay, and then we have the 0 at -15. Okay, so actually we also have the pole from the system at -4 and also the Z lead, Z 0, the same location at -4. Okay, so since that pole and 0 is on the same location, so we can have the zero pole cancellation. So the contribution of the angle will become 0 since that the angle contribute from the pole is negative value and the angle contribute from the 0 is the positive value. So that's why it is known as a zero pole cancellation. So we just can ignore the pole and this 0. And then we also have the P lead since that we want to find the location of P lead. So please remember to draw also the P lead. And then we draw the ST uncompensated and then draw the line between the post and zeros to the ST compensated. So after that, we evaluate the angle. So basically, we choose the right side. So actually, you can also choose the left side, but basically, I just choose the right side. So all on the right side. So from here, so you just imagine the triangle contribute for theta 1. So the triangle will become like this. So we need to find this theta 1. So the formula that we use here is a tangent inverse 3.31. So the distance between this to this divide by the distance between this to this. And the value here must be always positive. Kena positive because we consider the distance. Okay, same goes to the theta 2, but for the theta 3, since the triangle for the theta 3, when we draw the triangle for the theta 3 here, it become like this. So the formula to evaluate the theta 3 need to consider the 180 degree. Okay, and then we apply the formula, the summation theta 0 minus summation theta pole equal to minus 180 degree. So theta 2 here, so please remember theta 1, sorry, theta 1 is come from the zeros. Zeros. Oh, saya terbalik Ni salah. So ni ada mistake. So saya tertukar the angle. So this value should be the theta 1 since that theta 1 is our theta zeros. Okay, theta from zeros and the angle here should be theta 2. So nanti kita punya jawapan tengok 180 tambah 22.8 tolak dengan 14.29 tolak dengan 106.81. So dapat 81.7. Okay. So ni pun silap lah. So 81.7. So you will obtain the difference value for the P lead since that saya ada buat mistake dekat calculation. Okay. So after that we find the value of K lead. So K lead. So same with the K lag. So we will consider or we will include the Z lead and P lead. Okay, since that Z lead that we design here, same with the P from the system. So we can just ignore the Z lead and the P pole from the system at -4. So ada 3 ni sajalah. So here is from the system +1 +10, and here is our P lead, and the value here is the value from the system. Okay, then you just use your calculator, and lastly we write the transfer function of the G lead. Okay, boleh? Okay, next question. So a system is represented in a block diagram as shown in figure Q2. The system has an inner loop, a feedback, and a gain controller K is connected cascaded with the block of the inner loop feedback. So the uncompensated is given as T equal to -1.8 plus J 2.8 when a damping ratio of 0.545. The question asks us to evaluate the steady state error if the system operates with a damping ratio of 0.545 for a RAM input. Okay, so system here, so it is mentioned the system here is the system that connected with the K gain controller. K gain controller. So the question asks us to evaluate the steady state error if the system operates with a damping ratio of 0.545 for a RAM input. Okay, so what we need to find here is the steady state error. Steady state error. So we have a few formula for the steady state error. It depends on the type of our input. So sebelum ni, we use the formula ESS equal to 1 over 1 plus KP. So that is for the step input. But for this question, so the input given here is the RAM input. So we need to use the formula for the RAM input 1 over KV. Okay, 1 over KV. And then we need to find the value of KV. So the formula to find the value of KV is given by KV is equal to limit S to zeros KS. KS. So we have another S here, GS. Okay, so this is the formula to evaluate the KV. But when we want to apply the KV formula here, so we still didn't have the value of K. So we didn't have the value of K, so that's mean we need to find first the value of gain K. Okay, so like I mentioned before, so anything related to K, to find the value of gain K, so always goes to this formula. 1 over GS hash S, and we will replace as with the ST. So what is the value of ST that we need to use for this question? Since that the statement here, we use the K gain controller, and also the information or ST uncompensated is given. So uncompensated is always refer to the uncompensated system or the K gain controller. So here is the ST for the uncompensated or ST for the K gain controller. So we just use this value of ST to evaluate the K gain controller. Okay. Okay, so what is the value of G? G, since that the system here is the uh, complicated system. So before this, we only consider our calculation based on this system. So we have K cascaded with the G, and then we have feedback here. Okay, so this is the typical system. But for this question, so the system, so we have here what we call as a inner loop system. So you need to convert first this system to become to this system. So after we convert this system to this system, so after that we can use all the step or the formula that we already learned uh, in this chapter lah. So kena selesaikan dulu this system to become as this system. So that's mean from here. So we need to solve this inner loop system. So this is so actually very simple. So we have here this block cascaded with the 1 over S, and then we have a feedback path here. Okay, so so we do the closed loop here. The closed loop here, so GS here. So I put it as a, so you just write the forward path equation. So we have here S plus 5 forward path cascaded. So kita just darab sajalah S plus 2, S plus 12 multiply with 1 over S. I write it like this, 1 over S, and then we extend the divider here. Since that the feedback here is a negative, so P as a positive because of negative. And then we copy the equation on the numerator, so we only have 1. And then multiply with hash. So for this system, so our hash is equal to 30. So we multiply with 30. So that's mean this equation will become as the G. So we simplify the plot diagram, inner plot diagram here to become like this. So the value of T that we need to consider is the 1 over S plus 5, S plus 12 plus 30. Okay, so we just replace the equation. So no need to factor this equation. So you just can use this kind of equation into the K. Just masukkan saja. And then you just replace S with minus 1.8 plus J 2.8 and use your calculator. And then we can obtain the value of gain K. So after we obtain the value of gain K, so we can evaluate the value of KV. So I put it as a KV all. KV all refer to the KV uncompensated system. Okay, so we have S here. So we just okay, kita boleh potong dekat sini the value of S and then replace the value of gain K that we obtain. So the answer for the KV is 1.33. So after that, we can evaluate the ESS. 1 over KV. Okay. So that is the answer for the first question for the first question. So next question. Mana soalan dia? Okay, kita dah jawab Kita dah evaluate the ESS. So now, you need to suggest and design a suitable controller that meet the following requirement. So requirement here is the damping ratio and the steady state error. Okay, so since that the requirement is on the steady state error, so means that we will choose the lag compensator. Kenapa kita tak pilih PI? Since that PI always want to reduce or always want to eliminate the ESS to become zeros. Okay, but the for this question, they ask us to just to reduce the ESS by factor of 10. Okay, reduce by factor of 10 means that in mathematical equation, so the ESS new, jangan darab reduce reduce we always divide 10. So ESS all divide by 10. Okay, so please remember, reduce means you need to divide by 10. So kalau you multiply with 10, so your error larger compared to the K gain controller. So sepatutnya kita nak reduce bukan kita nak semakin besar kita punya steady state error. Okay, reduce by factor of 10, so that's why divide by 10. So jangan pula divide by 2 because sebelum ni sentiasa divide by 2, so all the question you just divide by 2. So no, so please look at the design requirements. So for this question, they ask us to reduce by a factor of 10, so you need to divide by 10. Okay, so design the lag compensator. So first step, so we will write the G lag and the formula. So this is the key to design the lag compensator. The formula of KP. So since that the system use the RAM input, so we will use the KV. So KV new over KV old equal to Z lag over P lag. So that means we need to find the KV old and then we need to find the KV new. Okay, KV old is already found from question A. So dekat sini kita dah dapat KV old or KV uncompensated system. KV old, which is a 1.33. The next we need to find the KV new. Typing error, KV new. So KV new is always based on the design requirement. So this is our design requirements. After that we obtain the ESS new. Since that we know that the relationship between the ESS and the KV, so of course we can find the value of KV new. Ada salah tak? Kalau tengok equation ni ada salah tak? Salah tak? Ada ke? Awak tidur ke? Ada salah tak equation ni?
Not sleeping, we are here.
Huh?
Dia
It should
tak
be?
Not sleeping.
0.7519. Nilai tu 0.075. Itu lebih zero.
Salah, nilai ni salah.
Eh,
Nilai ni betul.
Betul lah.
Kat mana salah?
Tolak 1.
Sebaik ada yang jawab
Tolak
betul.
1.
Tolak 1. Since that the formula for KVESS is equal to 1 over KV. So no need to tolak 1. Okay? Yang saya tolak 1 tu because of saya just copy ESS untuk KP. Sebab KP ESS is equal to 1 over 1 plus KP. So that's why yang tadi tu salah. So no need to tolak 1. since the formula for the kV is given by 1 over kV. So the answer should be 13, 13.3. And then we just choose the P lag, so 0.1. Nak senang pilih je 0.1 for the P lag. So after that we can evaluate the Z lag. So ni sebab saya dah salah. So ada salah sikit lah. 13.3 divide by 1.33 multiply with 0.1. So the answer is equal to 1. Okay, for the Z lag. Okay, dekat sini pun ada salah sikit lah because saya ada salah, dah tersalah kira. Since that the answer here should be 13.3. Okay, so lastly we just write the G lag. Okay, itu saja untuk ESS. So I want you to remember, don't memorize the step. Sebab the step is actually different, depends on the question. But you need to organize your answer based on this question. The question. So first we need to find the KV oil. KV oil from this question, since that we already calculate the KV oil, so you just use this formula. But for the first question here, for the KP oil, so we didn't calculate yet the value of KP oil, so that's why you need to calculate the value of KP oil. So after that, we find the value of KP or KV new based on the design requirement. Okay. So next, choose the P lag. So we can obtain the Z lag. And lastly, calculate the value of gain K. And lastly, you need to write the final transfer function that you obtain. Okay. That's all for the lag compensator. So the key here is this formula. So after this formula, so we find the KV oil, and then KV oil is always referred to the KV uncompensated system or KV that use the K gain controller. So after that, we find the KV new. So KV new is based on our design requirement. Our design requirement. Okay. Okay, last question. The last question, so the same system, but for this question, the design requirement here, the first question asks us to design the key gain controller for a damping ratio of 0.545, and then you need to prove that the controller cannot achieve the settling time less than or equals 1.7 second. So dia bagi dekat sini system and root locus with the zeta line of 0.545. So the first question dekat sini dah cakap K gain controller. So tak payah fikir, tak payah propose another controller. So what you need to do is design the K gain controller. It mentioned here K gain controller. So like I mentioned seperti yang saya dah cakap sebelum ni, so for the K gain controller, so we will always use this formula. K is equal to 1 over GSHS. And we replace S with the ST. Okay, G here must be the G for this system. Kg for the system is referred to the G for this system. So but for this question, the system not in the form of this general form. So that's mean you need to simplify the system until you obtain in this kind of form. So actually we already solve for the G in question number 3. So this is the answer. Okay. So dalam this answer scheme, so the value of T here, so is equal to S power of 3 plus 70 S power of 2 plus 16 S plus 30. Okay, so ini saya expand the equation. So the equation is actually equal to kat sini. So bila saya expand dapat itu. So sama saja. So ini dapat apa? 119. So dapat 119. So I want to show you if you expand the equation into the polynomial form and without expand the equation. So I just put the equation like this into to find the value of gain k. So actually you will obtain the same answer. So no need to worry. So you will obtain the same answer 119. Okay. So we already answered the first question to design the K gain controller. So the second question here asks you to prove that the controller cannot achieve the settling time less than or equal to 1.7 seconds. Okay, since that the ST from the root locus is given by minus 1.8 plus T 2.8. So ST, we know that ST is equal to the general formula for ST is given by minus zeta omega n plus J omega D. Okay, so from here, so we have the value of zeta omega n is equal to 1.8. So then we apply the formula of TS to calculate the TS 4 over zeta omega n. So we obtain 2.2 seconds. So this is the proof that we can say that this controller cannot achieve the value of TS less or equal to 1.7 second. Since that the K here, we give you TS 2.2 second. Okay, so this is how we prove that the K gain controller not able to achieve the design requirement. Okay, so we already answered the question A. So now the question B. So suggest and design a suitable passive controller. So remember, kalau passive controller either lag or lead. So that means the following requirement. So now the requirement here is the settling time. So kalau if we look on the first the second question, the requirement is on the steady state error. So that's why we choose the lag compensator. But now the requirement here, design requirement here is the settling time. Settling time. So we know that settling time, TS, TP, and so on. So this is the characteristic that define on the transient. So that means we want to improve the transient response. So for the transient response, the most suitable passive controller is the lead controller. So lead controller, so we will choose the lead controller. And then for the lead controller, so we write the equation. So the key point for design lead compensator. So remember the key point to design the lead compensator is the ST compensator. So please remember. So kalau untuk lag, so we will always use the formula. We will always start with the formula KP or KV. So kalau KP new over KP old equal to Z lag over P lag. But for the lead, So the starting to design the lead compensator, so you need to obtain the ST compensator. Okay, so if the ST compensator is not given in the question, so you need to use the design requirement to obtain the ST compensator. So for this question, the ST compensator is not given. It's not given. So what we have here is the ST uncompensated. So ini adalah ST uncompensated, since that the root locus here is the root locus for the K gain controller. So the ST here is the ST uncompensated. Okay, so the design requirement here, ST must be equal or less than 1.7 second. So ni adalah ST apa? So our ST desired, right? Our TS desired, right? TS desired, so that means the TS here, the TS given here is our TS compensated. Our TS compensated. Our TS compensated, so you can choose any values that less than 1.7 second. So semua betul. Kalau pilih 1.7 pun betul, 1.6 pun betul. So for this example, so I choose 1.5 seconds. But you need to make sure, don't choose a very low of the TS. Tak boleh lah pilih sampai 0.9. Takut nanti when you design the system, so you cannot get the correct angle. So kita pilih sikit je lah. Kalau dia kata less than 1.7 second, so maybe you can choose 1.6 or 1.5 second. So for this example, so I choose TS 1.5 second. Okay, so after that we find the zeta omega n, then omega n, and lastly we find the omega d. So next, we can obtain the ST compensated. So after we find the ST compensated, so we choose. So from here, the pole location, either you can read the pole and zero location from this graph. Sini, nampak? Dia bukan nombor bulat pole location, since that the system is the system look like this. So you need to, when you want to draw the pole and zeros from the system, so you need to find the pole location. So how to find the pole location? So we already obtained the GS. So the GS, the new GS that we obtained from here. So you just use your calculator to obtain the roots of the s square plus 70s square plus 16s plus 30. So nanti bila you guna calculator, so you will obtain that the post location is located at minus 12.3, minus 4.1, and minus 0.6. Okay, so for this example, so I choose my Z lead equal to minus 12.3, since that I want to provide the zero pole cancellation. Okay, ataupun you boleh choose minus 4.1. So for this case, I choose minus 12.3. So we will have the zero pole cancellation. So for the next step, so we just consider the pole at minus 0.6. and the pole at minus 4.1, and then we have a P lead, and we draw the ST compensated location. ST compensated. So then next we evaluate the theta 1 here and theta 2. So theta 1, when we draw the triangle, so theta 1 is at here. So that's why the formula that we need to apply must be include the 180 degree. But for the theta 2, so the triangle will look like this. So no need to consider the 180 degree. Directly we can obtain the theta 2. And then we apply the formula. Okay, so you apply lah. So no no angle from the zeros. So that's mean the theta P lead is equal to 180 degree minus 116.79 plus 17.77. Okay. So you dapat theta P lead is about 7.54 degree. And then we find the location. So since that the value here less than 90 degree, so the P lead must be on the left side. So this is the P lead, our P lead, and this is the our ST. So ST is located at -2 plus J 2.67 minus 2.67 minus 2.67 plus J 4.1. Okay, so we have here the value of theta P lead. Okay, so rearrange the equation so until you obtain the location of P lead. So lastly, we write the full transfer function for the G lead. Okay, so before that, we need to calculate the value of gain K. So for the gain K, so we only consider the post from the system at 0.6 and 4.1. Okay, so this is from the P lead, Z lead, and the system Z lead already have the zero pole cancellation, and you will obtain the value of gain K. So lastly, so write the full transfer function of G lead. So that's all for the question 1. So you need to nanti cuba buat cuba buat. So I will upload the answer so you can check with your answer. So any question? Ada soalan tak?
Tak
Tak ada
ada.
soalan
Tak ada.
Tak ada So kita stop sampai sini. So nanti you boleh try to answer this exercise. So I will upload the correct answer later on YouLearn for you to check. So any question or anything you want to ask, so you can ask me later. Okay, that's all. Thank you.
Terima kasih, Doktor.
Okay, sama.
Selamat Raya.
Selamat Hari Raya.
Thank you, Doktor. Selamat Raya.
Thank you. Selamat Hari Raya.
Thank you very much,
Terima
Doctor.
kasih, Doktor.
Thank you.
Thank you, Doktor.